The next definition on the handout is the concept of norm. Norm is a way to mathematically capture the intuitive notion that we have of size. So now while inner product is more important as far as linear algebra goes, especially since that one property was linear, it's a linear product, norm is easier for us to usually wrap our minds around even in abstraction. It's because we're used to talking about the size of things. And there are various ways to measure sizes of things, and so instead of talking about each different way to measure sizes of things on its own, we can capture those properties in these three, and that way whenever we talk about a norm, whatever we say about a norm applies to any different way of measuring the size of something. So those three abstract properties are that, first of all, the size of something is positive. We don't measure size in positive or negative, it's just always a positive, a measure. And in fact, the only thing that can have a non-zero, or that can have a zero size would be zero itself. Anything non-zero we say has a strictly positive measure, or size, or norm. The second property is positive homogeneity. What you should do is you should write on your handout, underneath positive homogeneity, write the word scaling. That property says that when we scale something, like double it or quadruple it or halve it, if we notice that on the inside of the norm there's an alpha u. That's scaling inside the norm. The result, the other side of the equal sign, is that we basically scale the size. If we double a vector, that's like doubling the length of the vector. If we have something, we have the size of it. If we scale something by a negative quantity, like a times -2, notice that flips the direction of things. But as far as the size goes, size being a positive measure, that absolute value on the right-hand side of that equation, or that alpha on that side of the equation, has absolute value on it. And that's because the size is always positive. If we multiply a vector by -1/2, it does flip, but the size is only affected by times +1/2. The last one there is called the triangle inequality, and that's the way to think of that is that u plus v on the inside of the norm, that is like the hypotenuse of a triangle. If you travel u in one direction and v in a different direction, the net result is that you've made a triangle. The resultant is the hypotenuse, or the third leg of that triangle, even if it isn't a right triangle. And that just says that that net result has to be less than the sum of the sides, the two sides that made up that triangle. There's one other note there, that anytime we have an inner product, there's already a natural norm, or meaning that we have a measure of size. The inner product of something with itself satisfies all three of those properties, and you should check that on your own sometime. So we started with inner product because that's more foundational, and we see that as soon as we have inner product, we also have bonus, this concept of norm or size. This then, inner product and norm, is the foundations for our geometry of linear algebra.